the wall that should not exist. It appeared first as a pattern in numbers, not in the sky. In a dark control room long after midnight, a group of astronomers stared at a map of the universe that was never supposed to look like this. On their screens was a structure made of galaxies, not a single cluster, not even a supercluster. It was a vast, tangled band of matter stretching across billions of light years, a feature so large that, according to the standard models of cosmology, it should almost be impossible. It later became known as something like the Hercules Corona Borealis Great Wall. The name sounds poetic. The reality is disturbing. This structure spans on the order of 10 billion light years. In other words, light would have to travel for most of the age of the universe just to cross it. The thing is, the early universe was supposed to be smooth. Tiny ripples in density, yes, but no preferred directions, no gigantic walls tying distant regions together. Gravity needs time to pull matter into shapes this large. There has not been enough time. Here is where things get uncomfortable. The equations that describe how galaxies form and clump together can handle big structures. Filaments, voids, superclusters. But when scientists ran the numbers for something this size, the result was simple. This should be vanishingly rare, or simply not there at all. Yet there it was, a pale arc of colored pixels on a monitor representing hundreds of thousands of galaxies, all stitched into one cosmic scar. In the room, no one heard anything except the quiet hum of cooling fans and the soft clicks of keyboards. For a while, they checked for errors, bad data, instrument glitches, statistical flukes. Because the scary part is not that the wall might be a mistake. The scary part is what it might mean if it is real. The incredible part was how subtle it looked. To a casual glance, just another feature in an already busy map of the cosmos. But the longer the scientists stared, the more it felt like a fingerprint pressed into the fabric of space itself. A fingerprint from what? If the universe grew from a tiny, nearly uniform state, what could have pushed on it hard enough to leave a mark this big? What kind of event could reach across billions of light years and rearrange galaxies like dust along a shock front? They had no idea. And that is pretty disturbing. Some physicists began to whisper a different possibility. Maybe this is not just an internal accident. Maybe it is a scar left by something outside the part of reality that can be seen. A boundary interaction, a collision, a scrape against whatever lies beyond the universe's horizon. If that is true, then this wall is not just a structure. It is a message, a hint that the story of the universe has already brushed against something larger, and almost no one recognized the moment it happened. That message leaves one immediate question hanging in the dark. A message from where? The scary part is that in modern cosmology, that question does not just have a disturbing answer. It might not have a valid meaning at all. The thing is, in standard physics, the universe is not a ball sitting in a bigger space. It is the space, all of it. Distance, direction, and time are not laid on top of some larger stage. They are the stage. Asking what is outside space-time is like asking what is north of the North Pole. The words fit together, but the result was not designed to describe anything real. Here is where things get uncomfortable. Astronomers still talk about an observable universe with a radius of about 46.5 billion light years. That sounds like an edge. It is not. It is a deadline imposed by light. Imagine standing in the middle of a lightless ocean with a single flashlight. Wherever the beam reaches, there is a visible bubble. Beyond that, the water continues, indifferent and unseen. The boundary is not a wall in the ocean. It is a limit in the beam. In other words, the observable universe is only the region from which light has had time to reach us since the Big Bang, while space itself has been stretching underneath it. For a while, that sounds manageable, just more water in the dark. But beyond can mean several different things, and each one is more unsettling than the last. Beyond what can be seen, there may be endless more galaxies, forever cut off by the speed of light and the expansion of space. Beyond our space-time, inflation theory hints at other bubbles, entire universes with different properties. Beyond our laws of physics, some models point toward higher dimensional structures or a quantum foam that does not even care about familiar ideas like space, time, or cause and effect. The incredible part was how quickly this escalates from astronomy into something that looks like existential horror. What would have happened if the universe had slightly different laws? In many of these scenarios, it did. Those versions simply never last long enough to notice. This episode will follow that descent in stages. First, the hard horizon of what can be seen. Then, the possible global shape of space, including disturbing wraparound topologies with no edge at all. After that, the multiverse ideas born from eternal inflation. Finally, the ultimate fates, heat death, vacuum decay, and whatever might lie beyond even those endings. With each step, the concepts move further away from anything human brains evolved to picture, and closer to stories that feel like cosmic horror, written in equations and background radiation. Somewhere past that flashlight's reach, the next clue is already waiting. That next clue comes with a hard stop. There is a point in the sky beyond which light itself has never reached us, and never will. Not because nothing is there, but because the universe will not allow that information in. Astronomers give it a calm name: the observable universe. In other words, the region of space from which light has had time to arrive since the Big Bang, 13.8 billion years ago. It forms a sphere around Earth with a radius of about 46.5 billion light years. That number is already disturbing. The cosmos is 13.8 billion years old, so how can anything be 46.5 billion light years away? The thing is, that distance is not how far the light traveled through empty frozen space. It is how far the space between has stretched while that light was in flight. Picture a time lapse of the entire universe. At the beginning, everything is compressed and blindingly hot. Galaxies have not formed yet. Then space starts expanding, slowly at first, then faster, pulled by dark energy. The camera keeps pulling back. Structures grow, clusters form, and distant galaxies race away. For a while, their light still climbs toward us, step by step, across the growing gap. But here is where things get uncomfortable. Eventually, the expansion between certain regions accelerates so much that even light, moving at the universal speed limit, cannot close the distance anymore. On the time lapse, those galaxies do something strange. They do not hit a physical wall. They simply fade, as if dragged over an invisible horizon. Their last photons arrive, dim and red stretched by expansion, and then nothing new ever follows. This invisible boundary is the cosmic horizon, a moving limit in space-time beyond which events are permanently cut off from any influence on Earth. No future telescope, no matter how advanced, can reach past it, because the problem is not sensitivity. It is geometry. The scary part is that this is not just a limit on what can be seen. It is a limit on what can ever be touched, visited, warned about, or escaped from. There are regions of reality whose light will never reach here, no matter how long the universe lasts. Scientists have run the numbers. The result was unsettling. Most of the universe is already outside that horizon, or destined to slip beyond it. Galaxies that are visible today are, in the long run, already lost. The incredible part was how final this is. This is not a temporary communication blackout. This is the structure of space-time writing a permanent no around almost everything that exists. And there is one more detail that is pretty disturbing. If something unimaginably powerful began beyond that horizon and started racing toward this region of space, the first sign would not be a warning glow on some distant detector. It would be the moment it arrived. Whatever that is, if it already started, it is on the way right now and completely invisible. There is another problem hidden inside that invisible threat. Even if nothing ever arrives from beyond, this region of space is already trapped behind a different kind of boundary. At first, it seems simple. There is a limit to how far light has had time to travel since the Big Bang. Beyond that distance, no signals have reached this part of the universe yet. In other words, there is a moving shell around everything that has ever happened here. Cosmologists give it a more technical name. It is called a cosmic event horizon. This horizon is not a physical wall. It is a one-way boundary drawn by the expansion of space itself. Information, light, and entire galaxies can cross outward over it, but once they do, no message, no particle, no spacecraft can ever cross back in. The thing is, this is not because those galaxies are moving through space faster than light. It is because the space in between is stretching. The result was a kind of cosmic conveyor belt that pulls distant regions away faster than any signal can chase them. Imagine two ships on a dark ocean talking over radio. For a while, the voices come through clearly. Then one ship drifts far enough away that Earth's curvature gets in the way. The signal fades, then dies. Nothing dramatic happens on deck, but the connection is gone. The universe does something similar, but the curve is space-time itself, pulled by dark energy. A galaxy can be shining, alive with stars, and yet its last photons are already on the way to crossing that invisible line, never to be replaced. Here is where things get uncomfortable. Galaxies beyond a certain distance are not just very far away. They are causally disconnected. No experiment, no future technology, not even a probe launched at almost light speed can ever reach them, no matter how long it waits. The scary part is, this prison is shrinking from the inside. As cosmic expansion accelerates, more and more galaxies are slipping over that horizon forever. One by one, their light redshifts into darkness, like distant city lights winking out in a growing fog. From this region of space, there are already galaxies that will never be seen again. Their last photons have passed. Their final messages have expired. For any observers born later, it will be as if those entire island universes never existed. The incredible part was how late this was understood. For most of human history, the night sky looked endless and eternal. Now scientists can calculate the timeline of disappearance. Eventually, almost everything will be gone from view. Only a tiny, gravitationally bound island of nearby galaxies will remain visible to distant future astronomers, floating in an apparently empty cold void. They will look out and see darkness in every direction, and the disturbing question will be unavoidable. If an entire universe can slip out of sight like that, what else is already missing beyond the horizon that defines this one? There is another problem hiding inside that darkness, a numbers problem that should not work but somehow does. The observable universe has a radius of about 46.5 billion light years. Yet the universe itself is only around 13.8 billion years old. In other words, light has had less than 14 billion years to travel, but the edge of what can be seen sits more than 3 times farther away than that distance would allow. At first glance, this looks impossible. Nothing can move faster than light, so how can anything be 46.5 billion light years away and still be visible at all? For a while, even scientists framed it as a kind of paradox. It sounds like galaxies must have somehow broken the speed limit. But the thing is, that is not what is happening. The galaxies are not racing through space faster than light. Space itself is stretching, carrying them along. The distances between everything are growing, even if the objects themselves are mostly just drifting. A simple picture helps. Imagine dots on the surface of a balloon. At first, they are close together. As the balloon inflates, the dots move apart, not because the dots are crawling across the surface, but because the surface itself is expanding. The incredible part was how well this simple idea matched what telescopes were actually seeing. Or think of raisins in rising bread dough. As the dough swells in the oven, every raisin sees every other raisin moving away. The dough is not backdrop. It is the thing that is changing. Here is where things get uncomfortable. In this analogy, space is the dough. Now add one more disturbing detail. Light leaving a distant galaxy billions of years ago did not cross a fixed gap. It has been chasing a target that has been running away the entire time. While that light was in transit, the space in between kept stretching, pulling source and destination farther apart. The result was that the light still arrives, but the current distance to that galaxy is far larger than time multiplied by speed. The journey that began when the universe was young ends in a cosmos that has grown far beyond the naive limit that intuition expects. The scary part is what this implies. If space can stretch this much inside the observable universe, what does it even mean to ask what lies outside that expanding fabric? Is there an edge the way there is an edge to a balloon? Or is the question itself broken? Eventually, this leads to a more unsettling possibility. Maybe the universe has no edge at all, and what lies beyond the visible horizon is not a boundary, but more of the same, hidden forever, no matter how deep the next generation of telescopes tries to look. If there is no edge in sight, the disturbing question becomes even sharper. If the universe is everything, what would an outside even mean? Most people carry a quiet picture in the back of their minds. The universe as a gigantic glowing sphere hanging in a much larger blackness. Galaxies on the inside, nothing on the outside. A clean shell with a definite center and a final sharp boundary where existence just stops. It feels simple. It feels obvious. And the scary part is, almost everything in everyday experience trains the brain to expect exactly that. Rooms have walls. Planets have surfaces. Even clouds have edges when they fade into blue sky. So the imagination just scales that up and gives the entire cosmos a skin. The fine print of the void. The anomalies. If the Great Walls are the skeleton of the universe, these facts are the ghosts in the machine. The dipole repeller. The invisible hand. For decades, we knew we were being pulled toward the great attractor. But in 2017, astronomers realized that gravity isn't the only thing moving us. We are also being pushed. Behind the Milky Way lies a vast, nearly empty region of space called the dipole repeller. It acts as a cosmic anti-gravity source, effectively shoving our entire local group of galaxies across the void. We aren't just falling toward a destination, we are being exiled from a wasteland. The axis of evil. The cosmological principle states that the universe should look the same in every direction, isotropy. However, the Planck satellite confirmed a terrifying alignment in the cosmic microwave background. There is a preferred direction in the temperature fluctuations of the early universe, a line that seems to align perfectly with the orientation of our own solar system. Scientists jokingly named it the axis of evil because it threatens to dismantle every model we have. It suggests that the universe has a top and a bottom, or worse, that our tiny corner of space is somehow at the center of a grand design we don't understand. Quasar synchronization. In 2014, astronomers discovered something that shouldn't be physically possible: large-scale quasar alignment. They observed 93 quasars, supermassive black holes, separated by billions of light years. Despite being so far apart that they could never have communicated or influenced one another, their axes of rotation were perfectly aligned. They are spinning in ghostly choreography, as if they are all being governed by a single, invisible thread of physics that spans the entire observable horizon. The lithium problem. Our math for the Big Bang is almost perfect, except for one glaring error: the missing lithium. When we look at the oldest stars, they contain only a third of the lithium-7 that Big Bang nucleosynthesis predicts should exist. It's as if a massive chunk of the universe's original starter kit simply vanished. This isn't just a rounding error. It suggests our fundamental understanding of nuclear physics, or the first 3 minutes of time, is missing a catastrophic variable. Dark flow. Beyond the expansion of the universe, some clusters of galaxies appear to be caught in a current. They are moving at millions of miles per hour toward a specific patch of sky between the constellations of Centaurus and Hydra. This dark flow doesn't follow the expansion of space. It's as if something outside the observable universe, something massive enough to exert a gravitational tug from beyond our ocean of light, is reeling us in. These anomalies suggest that the walls we see are only the beginning. The scary part isn't just that the universe is big, it's that the rules we've written to explain it might only apply to our specific, tiny, and perhaps biased bubble of reality. If you move far enough to the left or right, the laws of physics might simply change. Here is where things get uncomfortable. Standard cosmology says that picture is wrong in almost every detail. To see why, imagine a balloon, not the rubber, but only the two-dimensional surface. Now shrink intelligent ants down onto that surface and erase any idea of up or down. For the ants, their whole universe is that curved skin. They can walk in any direction, measure distances, draw maps. From the ant's point of view, there is no center on the surface. The center exists only in a higher dimension, in the air outside the balloon. There is also no edge for them to fall off. They can walk forever and eventually loop back to where they started without ever seeing a boundary. The result was a finite world with no wall, no rim, no outside they can reach. The thing is, in modern physics, space is not just an empty container. It is a dynamic fabric of space-time, shaped by mass and energy. In other words, the universe is not a bunch of stuff sitting in space. The universe is the space-time itself, plus everything woven into it. According to the current best models, that fabric does not come with a marked line where it simply ends. There is a horizon beyond which light has not had time to reach us, but that is not a wall. It is a limit on information, not a cosmic fence. So, what would it even mean to ask what lies outside spacetime? Mathematically, it breaks the coordinates that define the question. It is like asking what is north of the North Pole. On a globe, every direction from that point is south. North of north is not a mysterious hidden country. It is a request that geometry refuses to answer. And yet, this is where things slip from abstract to pretty disturbing. Because if there is no edge, if there is no outside, why do some observations hint at something pressing in on this balloon like fabric from beyond? Strange alignments in the cosmic microwave background, enormous galaxy walls that should not exist, cold spots that look like bruises on space-time itself. For a while, many scientists dismissed them as noise. Eventually, others began to ask a different question. If nothing is outside the universe, what would have happened if something left a scar anyway? Those scars raise a quieter, more disturbing question. Not just how big the universe is, but what shape the whole thing actually has. In simple terms, there are three main options: a flat universe where parallel lines stay parallel forever, a positively curved universe like the surface of a sphere where lines eventually meet, and a negatively curved universe like a saddle where lines drift apart. These are not just abstract drawings from a textbook, they are different possible fates for everything. To figure out which one reality chose, scientists turned to the oldest light in existence, the cosmic microwave background. It is the afterglow of the Big Bang, stretched into microwaves by 13.8 billion years of expansion. By measuring tiny temperature variations in that glow, missions like WMAP and Planck tried to see whether space itself bends on the largest scales. The result was unsettling. Space, as far as those measurements can tell, is extremely close to flat. Not perfectly, just close. The scary part is hidden in the error bars. Those tiny uncertainties still leave room for a universe that is very slightly curved or wrapped in a topology that the data cannot easily expose. Here is where things get uncomfortable. A flat-looking universe does not have to be infinite. A sheet of paper can be rolled into a cylinder. A cylinder can be joined into a torus, a donut shape. Locally, every small patch still looks flat. In other words, space could be finite in volume, yet have no edge anywhere. A useful analogy is the two-dimensional surface of Earth. An ant can walk in any direction and never hit a wall, yet the total area is limited. There is no boundary line in the dirt that says, end of world. A three-dimensional version of that idea is a finite but unbounded universe. No edge, no outside, just a closed shape existing on its own terms. The incredible part was what this implies for travel. In some possible cosmic topologies, moving in a perfectly straight line for long enough would eventually bring a spacecraft back to its starting point from behind without ever turning around. Space would loop back on itself. If that sounds abstract, consider what it means for light. If space can wrap, light can too. Photons from a single galaxy could circle the cosmos and arrive from multiple directions at different times, painting the sky with ghost copies of the same object. The night sky could already be full of repeats, mirrored across the heavens, and for a while, scientists had no idea. And if the universe is quietly echoing its own contents, the next question is worse. What if some of those echoes are not from this universe at all? Imagine flying a perfectly straight line through space, engines never shutting off, no turns, no shortcuts. Then, after an unimaginable time, the stars ahead begin to look strangely familiar. In this scenario, nothing has glitched. Space itself has. because in one disturbing class of models, the universe is not an endless open expanse. It is finite, wrapped, and connected back on itself, shaped like a three-dimensional torus. In other words, like the surface of a donut, but extended into all three spatial dimensions. Go far enough in one direction, and the result was simple but unsettling. Return to the starting point from the opposite side. On a flat map, this looks like an old video game. Exit through the right edge, reappear on the left. But here is where things get uncomfortable. Every straight path in space eventually loops. Light does the same thing. Photons leaving a distant galaxy could circle the cosmos again and again, arriving from multiple directions at different times, carrying different snapshots of the same object's past. The sky in that case would become a literal hall of mirrors. The same galaxy cluster might appear in front, behind, and overhead, each image at a different distance, each one showing a different age. A single event, like a supernova, could echo across the heavens as if many different stars were dying, when in reality it was just one, seen over and over. The scary part is that nothing in everyday observation would immediately give this away. Everything would still look like a normal, vast universe. And once the structure of space itself starts hiding beyond the horizon, it raises a darker possibility. Maybe what lies past that boundary is not just more of this universe, but something entirely different. So the horizon might only be the edge of what can be seen. But in the faint afterglow of the Big Bang, there is something that suggests the story might be much stranger. Spread across the entire sky is a nearly uniform bath of invisible light. It is cold, only a few degrees above absolute zero, and it comes from every direction at once. This is the cosmic microwave background, in other words, the cooled down echo of the moment the early universe first became transparent. For a while, scientists thought it was almost perfectly smooth. Almost. When missions like COBE, WMAP, and later the Planck satellite started mapping this radiation in detail, a pattern emerged. Tiny temperature fluctuations, a few millionths of a degree hotter or colder than average, speckled the sky. Those ripples were expected. They are the seeds from which galaxies eventually formed. The result was a kind of cosmic baby picture, noisy but statistically well behaved, except for one region. In the southern hemisphere of the sky, WMAP and Planck both saw a broad patch that was different, colder, darker in microwave light, and much larger than the surrounding variations should allow by random chance. This became known as the CMB cold spot. The scary part is, it is not a tiny glitch. It spans hundreds of millions of light years in projected size. On the maps, it looks like a bruise. Mainstream explanations came quickly. Maybe it was just a statistical fluke, an unlikely but not impossible roll of the cosmic dice. Maybe a huge underdense region of space, a so-called super void, sat between this universe and that part of the background, draining energy from the microwaves through something called the integrated Sachs-Wolf effect. For years, surveys hunted for that void. Hints appeared, but nothing quite big enough, deep enough, or clean enough to close the case. Here is where things get uncomfortable. None of the conventional ideas are completely satisfying. That opened the door to something far more disturbing. A few theorists suggested the cold spot might not be an internal defect at all. Instead, it could be external damage. In some inflation models, this universe is just one bubble in a larger inflating space. If two such bubbles collided in the first fractions of a second, the impact could leave a circular scar in the cosmic microwave background. The incredible part was that the predicted signature of such a collision looks eerily similar to a large, anomalous cold region, like a bruise from another universe. If that is even close to true, it raises a different question. What kind of process can keep creating new universes like bubbles in boiling water? And, more disturbing, what would have happened if another bubble had hit this one later, when stars and galaxies already existed? For cosmologists studying inflation, this is not just ancient history. Some versions never really stop, which means the thing is, the mechanism that may have spawned this universe might still be running, somewhere beyond the horizon right now. Inflation began in a place so small that, in a sense, there was no place yet at all. Picture everything that would ever become galaxies, stars, planets, and living things compressed into an unimaginably tiny, hot, dense region. Not the size of a planet or a mountain or even a grain of sand, much smaller than a single proton. Then, in a sliver of a moment, that region did something deeply disturbing. It ran away from light. During a phase called cosmic inflation, space itself started expanding at an exponential rate. In other words, it did not just grow, it doubled, then doubled again, and again, over and over in a time so short that light, the fastest thing allowed in the universe, would not have had time to cross an atom. The incredible part was that nothing inside space had to break the cosmic speed limit. The rule, nothing moves faster than light, applies to motion through space. Inflation was space itself swelling beneath everything, dragging matter and radiation apart on a stretching fabric that refused to stay still. To explain what drove this runaway expansion, scientists use a placeholder, the inflaton field. Not a specific particle, not a machine hidden in space, but a kind of energy field filling that early universe. As long as the inflaton sat in a high energy state, it pumped space with repulsive gravity, forcing it to double again and again. When that energy finally decayed, inflation ended locally, and a hot, dense, more familiar Big Bang fireball took over. Here is where things get uncomfortable. In many models, the inflaton does not switch off everywhere at once. In some regions, it decays and inflation stops, creating a bubble like the one that became this observable universe. In other regions, it keeps going. Space there continues to inflate, faster and faster, pulling those regions away beyond any possible contact. The scary part is that this process, called eternal inflation, never really ends. A region smaller than a proton can inflate to far larger than the observable universe in far less time than light needs to cross a single atom. And while that happens, new bubbles keep forming elsewhere. Each bubble cools, ignites its own Big Bang, and evolves its own galaxies. If it can, some might collapse almost immediately. Some might have completely different physical laws. The thing is, most of them will remain forever outside any horizon that this universe can see. From the inside, a bubble like this one feels complete. It feels like everything. But if inflation is right, this entire visible cosmos could be just one patch in a vastly larger, eternally inflating background. And that raises a disturbing question. If this is only a single bubble, what, if anything, lies beyond the foam? The disturbing answer many cosmologists now give is this: beyond the foam, the boiling never stops. In the standard picture, the early universe went through a brief, violent growth spurt. Space didn't just expand, it ballooned faster than light in a fraction of a second. This runaway stretching is called inflation. But in some of the most influential models, inflation doesn't end everywhere at once. It shuts off in patches. It keeps going in others. The result was not a single universe calmly coasting outward, but something much stranger: eternal inflation. In other words, the background space keeps inflating forever, while isolated pockets drop out of that phase. Each pocket stops inflating, heats up, and explodes into a hot, dense fireball. To any observers that eventually form inside, it looks like a big bang. It looks like the beginning of everything. Those pockets are called bubble universes. Each one is a region where inflation ended and normal cosmic expansion took over. Inside, particles condense, atoms form, stars ignite. Physical constants can, in principle, take different values from bubble to bubble. The strength of gravity, the charge of the electron, even the number of spatial dimensions could be different. The scary part is that this turns reality into a kind of cosmic lottery. Most bubbles might be sterile or short-lived. A few, by chance, have conditions that allow galaxies, planets, and conscious observers. The result was a multiverse that looks less like a grand design and more like an endless series of doomed experiments. The thing is, there is a simple way to picture it. Imagine a pot of water on the edge of boiling. At first, the surface looks smooth. Then tiny bubbles appear. Some vanish. Others grow, rise, and collide. All the while, the water between them is still roiling, still gaining energy. Now replace the water with inflating space. The bubbles are universes. The surface of each bubble is like a frontier where inflation has ended on the inside, but rages on outside. New bubbles keep forming in the surrounding foam, even as older ones expand internally for billions of years. From the inside, an entire observable universe is just a minuscule patch on that bubble's surface. Everything ever seen with telescopes, every galaxy cluster and cosmic void, would be a local detail on one droplet in an endless cosmic boil. Here's where things get uncomfortable. In eternal inflation, there is no center, no preferred bubble, and no final one. And it gets worse. In this picture, bubbles do not live in isolation. They can, under the right conditions, collide. The incredible part was that this isn't just abstract philosophy. Some scientists have spent years combing the cosmic microwave background for circular scars, faint imprints that could be the aftermath of another universe slamming into ours. If that ever happened, what would have happened to everything familiar? Somewhere in that infinite foam, a collision like that is almost guaranteed. And if it already occurred here, the evidence might still be written across the sky, waiting to be recognized. In the multiverse picture, a collision between universes is not a poetic metaphor. It is a literal impact. Imagine two regions of space, each born from inflation, expanding like bubbles in a boiling cosmic foam. Eventually, their edges touch. In that instant, the smooth expansion breaks, and a violent, sweeping boundary forms where their versions of physics crash into each other. In simple terms, it is two different rule books for reality slamming together at relativistic speed. The result is a kind of shock front, a wall where temperatures spike, fields oscillate, and the basic constants that quietly govern matter on one side do not quite match the ones on the other. From inside a bubble like ours, that impact would not look like a Hollywood explosion. It would look like geometry. Observers would see a preferred direction, a circular imprint burned into the oldest light in the universe. That ancient light is the cosmic microwave background. It is the afterglow of the Big Bang, stretched into microwaves by billions of years of expansion. In an undisturbed universe, its tiny temperature variations form a random speckled pattern. But a bubble collision would carve something else into it, a disk, a bruise on the sky. The scary part is that this bruise would not be dramatic to the naked eye. It would be a subtle anisotropy, a slightly warmer or cooler circle tens of degrees across, its edge just a little too sharp, its internal pattern just a little too ordered. For a while, scientists have been combing satellite maps from missions like WMAP and Planck, running algorithms that search for these circular scars. They look for statistical anomalies, regions where the fluctuations line up in improbable ways. Some teams have reported hints, low significance rings that refuse to disappear completely in the noise. Here's where things get uncomfortable. Those hints are tantalizing but inconclusive. The same data can often be explained by random chance or by more mundane effects like foreground dust and instrument noise. In other words, the sky is whispering, not confessing. But if a collision did happen early in cosmic history, the incredible part was not just the mark it left. In principle, the impact zone could be a place where the vacuum state itself changed. That means the laws of physics could be different there. Particle masses, interaction strengths, even the stability of atoms. Push that idea further, and it becomes pretty disturbing. A sufficiently violent collision sweeping through a region could rewrite reality as it goes, converting one vacuum into another, erasing galaxies, planets, and any observers without leaving survivors to tell the story. The thing is, such a collision front would not respect the observable universe as a boundary. It could already be racing toward this bubble from beyond the horizon, moving effectively at light speed through space that is still expanding. From inside, there would be no advance warning, no precursor signal crossing ahead of it, no subtle gravitational tug announcing its approach. The first sign would be the last, the local laws of physics failing in the instant the front arrives. So when cosmologists talk about bubble collisions, the question is not just whether a bruise exists somewhere on the microwave sky. It is whether one of those invisible impact zones is already inbound, hidden forever beyond what any telescope can see, closing the book on this universe before anyone even realizes the story is over. So the universe might already be living on borrowed time with no warning at all. To cosmologists, that makes the night sky look less like a peaceful ceiling and more like a frozen crime scene. The main event, the Big Bang, and whatever triggered it, is over. The fire, the impact, the original violence is long gone, but the evidence is still scattered everywhere, locked into light, temperature, and structure. In other words, the universe is a cold case. The suspects are unknown. The weapon is the laws of physics themselves. And every observation is another photograph of the scene taken billions of years after the fact. The faint microwave hiss between TV channels, that is not just noise. It is the afterglow of the Big Bang, stretched into the cosmic microwave background. To investigators of the cosmos, that glow is a fingerprint dusted across the entire sky. Tiny temperature variations in it, differences of a few millionths of a degree, are like ridges and whorls, precise patterns left by processes that happened when the universe was only 380,000 years old. Zoom out to the distribution of galaxies, and the picture turns darker. Clusters, filaments, and vast empty voids form something that looks disturbingly like blood spatter mapped across three-dimensional space. The result was not random. Gravity, dark matter, and dark energy pulled and stretched matter into these shapes, creating structures hundreds of millions of light years long. The scary part is that some of the stains do not quite match the official story. There is the CMB cold spot, a region of the microwave background that is significantly cooler and larger than expected. For a while, some scientists wondered if it was a cosmic bullet hole, evidence of a collision with another bubble universe punched through the fabric of this one. Then there is the so-called axis of evil, an eerie alignment of large-scale CMB features along a single direction in the sky. It should not be there in a perfectly random, isotropic universe. Yet it is. Pretty disturbing for a model that assumes no preferred direction in space. On even larger scales, astronomers have mapped walls of galaxies so huge they strain current theories, like the Sloan Great Wall and other megastructures. These look like impact spray frozen in time, as if something slammed through the early universe and left shock patterns behind. Here is where things get uncomfortable. Most of these anomalies probably have mundane explanations: statistical flukes, measurement issues, incomplete models. Eventually, better data may erase them, but investigations stay open precisely because there is a small chance that one of these clues is real evidence of something beyond the standard story. And if this entire universe is just one crime scene, there is a deeper question waiting in the dark. Who or what set up the laws that every possible universe has to obey? One answer says there was no setup at all. It says the laws that feel so precisely arranged inside this universe might only be local rules inside a much bigger, much stranger structure. This is where fine-tuning enters the story. The thing is, the basic numbers of physics do not look random. The strength of gravity, the charge of the electron, the mass of the proton, the tiny cosmological constant that makes space expand faster over time. Change any of them by a little, and the result was not a slightly different cosmos. It was no meaningful cosmos at all. Imagine gravity a bit stronger. Matter clumps faster, stars burn hotter, galaxies collapse on themselves before heavy elements can spread. Imagine it weaker. Gas never pulls together, no stars ignite, just a thin, cold fog expanding forever. In other words, either everything falls in too quickly, or nothing really forms in the first place. The same goes for the cosmological constant. Make it only a fraction larger, and space races apart so fast that galaxies never assemble. Make it smaller or negative, and the universe recollapses into a dense fireball long before complex chemistry has a chance. For a while, scientists tried to adjust models to make these numbers feel less unlikely. The scary part is that most attempts only made the coincidence look worse. Here's where things get uncomfortable. One explanation does not change the numbers. It changes the context. In the theory of eternal inflation, space does not just expand. It keeps spawning new regions, like bubbles boiling in an endless cosmic foam. Each bubble cools with its own settings for those fundamental constants. Most of those bubbles would be instant failures. Universes that rip themselves apart in moments. Universes that freeze into featureless darkness. Universes that collapse back into nothing almost as soon as they appear. The incredible part was the implication. If there are enough bubbles, then even outrageously unlikely combinations of constants will still occur somewhere. Observers can only appear in the rare bubbles where long-lived stars, stable atoms, and complex chemistry are possible. So of course, any conscious mind that asks why these numbers will always find itself inside one of the safe pockets. Anything else never gets to ask the question. That answer works. It removes the need for design. It also removes the need for this universe to be special in any deeper sense. In this picture, this entire visible cosmos is just one lucky ticket in an infinite lottery, and almost every other ticket is dead on arrival. If that is true, What would have happened outside this bubble is even more disturbing. Beyond the edge of what can ever be seen, there would be endless failed realities, silent, empty, forever unobserved. And somewhere among them, other bubbles as fragile and temporary as this one. And that raises a darker possibility. If bubbles can begin, can they also be erased by something coming from beyond their walls? In that landscape of fragile bubbles, most never get the chance to look anything like this one. Imagine a universe where gravity is only a little stronger, not dramatically, not cartoonishly, just enough. The result was brutal. Space begins to expand, matter starts to spread out, and then everything slams back together in a catastrophic recollapse. It all ends in a fraction of a second. There is no slow cooling, no gentle formation of atoms, no patient buildup of stars and galaxies. In other words, there is no time for structure at all. The entire history of that universe is one violent heartbeat. Birth, crush, silence. For a while, inflation theorists treated these as mathematical edge cases. Then detailed calculations showed something disturbing. These dead-on-arrival universes could be common. Now flip the dial the other way. Picture a universe where the cosmological constant is much larger. Space still starts hot and dense. But the scary part is that expansion wins instantly. Galaxies never form. Gravity never gets a chance to pull matter into stars or planets because the fabric of space stretches everything apart faster than anything can clump. What is left is a thin, cold mist of particles racing away from each other forever. No bright clusters, no night sky full of points, just an endless dim dilution. Here is where things get uncomfortable. By some estimates, universes like this, ripped open by runaway expansion, could vastly outnumber calm, slow-forming ones like ours. There are worse cases. Consider a universe where the basic constants of physics shift just enough that stable atoms never exist. Protons might decay too quickly, or electrons might never settle into reliable orbits. There is light, there is radiation, there is energy, but there are no atoms, no chemistry, no planets, no rocks, no clouds. Only featureless radiation and fleeting, unstable particles that fall apart almost as soon as they appear. The incredible part was how easily the equations allowed this. Change a few numbers and entire categories of reality disappear. Eternal inflation does not carefully engineer one friendly cosmos. It sprays out bubble after bubble with different settings, most of which are instantly lethal to complexity. Habitable universes become statistical outliers, tiny exceptions floating in an ocean of failures. The thing is, from inside a successful bubble, that brutality is invisible. Observers arise only where the settings already work, so any conscious mind looking around will see a universe that appears delicately tuned and surprisingly stable. They had no idea how many dead siblings were left behind, but that apparent safety might be temporary. Modern physics allows for something called vacuum decay, where the underlying state of space itself can suddenly change. If this vacuum is only metastable, a more stable version could appear somewhere as a tiny bubble and start expanding at almost the speed of light. No warning, no defense. And the next section asks a disturbing question. What if that bubble has already formed and is already on the way? Vacuum decay sounds abstract. It is not. In the language of modern physics, it is a very specific way everything ends at once. To understand it, the idea of a vacuum has to change. Empty space is not actually empty. It is filled with invisible quantum fields, stretching through every region of the universe, even the parts beyond any telescope's reach. The calm, featureless background between galaxies is really a kind of energy arrangement. Physicists call that arrangement a vacuum state. In other words, it is the lowest energy configuration those fields can sit in, the baseline against which everything else happens. Particles, atoms, stars, all ride on top of it. But here is where things get uncomfortable. The vacuum that currently fills the observable universe might not be the true lowest energy. It could be only metastable. That means it behaves as if it were the bottom, but it is actually a false floor. Imagine a ball resting in a shallow dimple on a hillside. It looks settled. For a while, nothing changes, but there is a deeper valley further down. A small push or a quantum fluctuation could send the ball over the lip and down into a much lower state. A metastable vacuum is that ball in the dimple. Vacuum decay is the event where that push finally happens. At some random point in space, a tiny region can tunnel through the energy barrier and drop into the true vacuum. The result was predicted decades ago in quantum field theory. A microscopic bubble of lower energy vacuum snaps into existence. The scary part is what happens next. That bubble does not just sit there. The difference in energy between the false vacuum outside and the true vacuum inside drives it to expand, inflating outward at nearly the speed of light. No shockwave, no fireball, just a silent, unstoppable front rewriting space itself. Inside that bubble, the rules change. The values of fundamental constants can shift. The masses of particles, the strength of forces, even the number of stable dimensions could be different. Chemistry, as it is known, fails instantly. Atoms may not be able to hold together at all. From the perspective of anything caught on the boundary, there is no time to react. No warning, no pain, not even a moment of awareness. One instant, familiar physics. The next, nothing recognizable. The event is both mercifully quick and pretty disturbing in its totality. The thing is, this process does not care about human scales or horizons. If a true vacuum bubble formed 1 billion light years away, beyond the edge of the observable universe, its boundary would still move at almost light speed. That means there is no way to see it coming in advance. The incredible part was the realization that if such a bubble has already formed anywhere in the wider cosmos, its approach is, in principle, undetectable. No instrument can look past the cosmic horizon to check. If a wave of altered reality is already on the way from beyond what can be seen, every plan, every model of the distant future becomes conditional. What would have happened if the universe were not metastable at all, but guaranteed to decay? Some physicists have quietly asked whether certain cosmic structures, such as enormous galaxy walls that should not exist, might even hint at past phase changes in regions forever separated from this one. For cosmology, that raises a different question. If this entire observable universe is just one vacuum phase in a larger multiverse, what lies beyond the bubble's edge when it finally pops? The next section turns to that possibility, that this reality is already just one region in a much stranger landscape. Imagine an ordinary Tuesday, traffic lights changing from red to green, a barista handing over a coffee, a child in a classroom tracing constellations on a worksheet that shows a calm, predictable night sky. Nothing seems unusual. The laws of physics are quietly doing what they have done for 13.8 billion years. Now freeze that frame. In that frozen moment, far beyond the edge of the observable universe, something has already started. A tiny region where the vacuum itself has slipped into a lower energy state. It begins as a microscopic seed. Then it grows. Physicists call this a vacuum decay bubble. In other words, a wavefront where the very rules that define particles, forces, and even the structure of atoms are rewritten. The scary part is that bubble does not crawl through space. It races outward at almost the speed of light. There's no warning line in the sky, no strange aurora, no gravitational tremor that hints at what is coming. From the perspective of that barista, that child, that driver at the light, there is not even time to turn ahead. One instant, the vacuum is the familiar false vacuum that allows stars, chemistry, and biology to exist. The next instant, the bubble wall arrives, and the vacuum becomes something else entirely. Here is where things get uncomfortable. If the new vacuum has different constants of nature, protons might no longer be stable. Electrons might not bind to nuclei. Light itself might propagate differently. The result was calculated in models. Matter as it is simply cannot survive. From inside the event, there is no sense of transition. No one feels themselves being torn apart. There is just normality. And then there is nothing that could register experience at all. Statistically, this has not happened here for a very long time. Our vacuum has persisted through 13.8 billion years of cosmic history. Galaxies have formed, stars have died, planets have cooled, and for a while that has given an illusion of safety. But longevity is not a guarantee. It only tells scientists that the decay rate, if it exists, must be low. It does not promise that the next second is safe. A bubble could already have formed in some unreachable region beyond the 46.5 billion light-year horizon, expanding silently through space that will never be visible. Most physicists think that given current measurements, vacuum decay is unlikely in the near future. Yet the thing is, no one knows if our vacuum is truly the lowest possible state. That uncertainty leaves a non-zero risk written into the fabric of existence. This is pretty disturbing on its own. A universe that can end without a sound, with no survivors, no ruins, and no last messages. The glitches in the code. The breaking of physics. If the previous anomalies were ghosts, these facts are the structural cracks in the foundation of reality itself. They suggest that our mathematical models aren't just incomplete. They might be fundamentally misinterpreting the language the universe is written in. The Hubble tension. The universe's two heartbeats. In science, if you measure the same thing using two different proven methods, you should get the same answer. But when we measure the expansion rate of the universe, the Hubble constant, we get two different numbers. Measuring the afterglow of the Big Bang gives us one speed. Measuring the distance to nearby stars gives us another. The discrepancy is statistically significant, meaning it's not a mistake. It's called the Hubble tension, and it suggests that the engine of the universe has changed gears in a way we cannot model. It is as if we are looking at two different universes that refuse to sync up. Strange matter, the ultimate pathogen. Deep inside the hearts of neutron stars, the pressure is so intense that protons and neutrons may dissolve into a soup of quarks. Some physicists theorize this creates strange matter, a substance so perfectly stable and dense that it is the ultimate state of existence. The scary part, strange matter might be infectious. If a single strangelet, a tiny piece of this matter, were to touch ordinary matter, it would instantly convert it into strange matter. A single grain could turn our entire sun into a small, cold, dead lump of strangelet in a matter of hours. It is the gray goo scenario on a subatomic cosmic scale. Cosmic strings, the cracks in space-time. When the early universe cooled, it may not have done so perfectly. Just as water freezing into ice develops cracks, spacetime may have developed topological defects called cosmic strings. These are one-dimensional cracks in the universe, thinner than an atom, but carrying the weight of entire mountain ranges in every centimeter of their length. They would stretch across the entire observable universe. If you were to encounter one, the gravitational distortion would be so intense it could slice through a planet like a wire through butter, leaving no trace of the impact except a perfectly severed world. The past hypothesis, the impossible beginning. The second law of thermodynamics states that entropy, disorder, always increases. This means the universe must have started in a state of impossibly low entropy, a state of perfect order that is mathematically so unlikely it borders on the miraculous. This is the past hypothesis. We have no explanation for why the Big Bang was so neat. If the universe had started just a fraction more messy, stars would never have formed, and the universe would have been a lukewarm soup of nothingness forever. We are living in the wake of a statistical impossibility. The Boötes Void, the great nothing. While most of space is empty, the Boötes Void is a super void 330 million light-years in diameter. Based on the density of the rest of the universe, it should contain roughly 2,000 galaxies. It contains fewer than 60. It is a hole in the web of the universe so large that if the Milky Way were in the center of it, we wouldn't have known other galaxies existed until the 1960s. Some fringe theories suggest it isn't a natural formation, but the result of an expanding Kardashev Type 3 civilization that has harvested the light of every star in its path, leaving a sphere of darkness in its wake. The scary part isn't that these things exist, it's that they suggest the laws of physics are more like local customs. We are trying to map a dark, infinite house by looking through a single keyhole, and we are starting to realize that the rooms we can't see don't follow the rules of the room we're in. If the vacuum itself can change, then what does beyond even mean? Beyond the observable universe, beyond this bubble, beyond a dead cosmos after decay. Does anything exist there in any recognizable sense, or does outside simply stop being a meaningful word? Picture two vast invisible sheets hanging in a dark, higher dimensional void. Each sheet is cold, almost perfectly smooth, and almost perfectly empty. On one of those sheets, every galaxy, every star, every planet is just a tiny vibration in the surface. Now imagine those sheets are not fixed. They drift, very slowly, over billions or even trillions of years. They move through the bulk, pulled by forces that cannot be seen from inside any one universe. The distance between them shrinks, but from inside, nothing looks different. No telescope can see sideways in this direction. To the inhabitants, everything seems normal. The scary part is that in ekpyrotic models, this slow approach ends the same way every time, with a hit. When the brains finally collide, the impact releases an enormous amount of energy into their surfaces. The result was a blinding, hot, dense state that from the inside would look exactly like a Big Bang. In other words, the beginning of time in this universe might really be a scar, a burn mark from a higher dimensional crash. Space inflates, matter forms, background radiation cools, and billions of years later, scientists stare at that radiation and call it the cosmic microwave background without seeing the collision that created it. Here's where things get uncomfortable. Some versions of this idea, called cyclic or cyclic ekpyrotic models, say that this does not just happen once. The brains separate after the collision. The universe expands and thins out. Stars die, black holes evaporate, everything drifts toward heat death, and eventually, the higher dimensional forces pull the brains back together again. A new collision, a new burst of energy, a new, hot, dense beginning. From the inside, it looks like a fresh Big Bang with no memory of what came before. From the outside, it is just another cycle in an endless series of ghost collisions in the bulk. The incredible part was how well some versions of this picture can be tuned to reproduce what telescopes actually see. A nearly uniform background, tiny temperature ripples, large-scale structure. For a while, this made some researchers wonder what would have happened if the last collision had been slightly different, a little closer, a little faster. Would the universe have been stable enough for galaxies at all, or would everything have torn itself apart? But there is a deeper problem. If the Big Bang was a collision, then the before lives in another dimension and in another phase of the brain's motion. Is there any way to see past that impact, to read the layers beneath the burn mark? Or is every observer permanently sealed inside the debris cloud of the last crash, with the next one already on its way from beyond the horizon? There might be no way to see past the crash, but what if the real beyond was never out there in higher dimensions at all, and was instead boiling beneath everything at the smallest scales reality allows? From far away, space-time looks calm. Galaxies drift, light travels, clocks tick. In the equations of general relativity, the fabric of the universe appears smooth and continuous, like an endlessly stretched sheet. The thing is, that picture quietly breaks down when the distances become unimaginably small. At around 10 to the minus 35 meters, the so-called Planck length, the rules of quantum mechanics stop treating space-time as a clean surface. The result was a prediction that is both mathematically reasonable and pretty disturbing. At that scale, space-time is not smooth at all. It is thought to be violently fluctuating, constantly twisting, stretching, and reconnecting in ways that no human instrument can directly see. Physicist John Wheeler gave this seething, unstable layer a name: quantum foam. From high above, an ocean looks flat and harmless. Ships glide across what seems like a simple blue plane, but drop down to the surface and the illusion dissolves. Waves slam into each other, whirlpools form and vanish, bubbles appear, pop, and are replaced by new ones in a chaotic cycle that never really stops. According to many quantum gravity models, space-time may be exactly like that. On cosmic scales, it looks like a quiet sea. Down near the Planck length, it behaves more like a storm, a frothing network of microscopic tunnels, loops, and bubbles of space-time itself, constantly forming and annihilating. Here's where things get uncomfortable. Even what seems like empty space inside the universe is not truly empty. Quantum field theory says that every point in space is filled with fields that never quite sit still. Virtual particles flicker into existence, interact for a moment, and then vanish again, borrowing energy from the vacuum and paying it back almost instantly. For a while, many scientists treated this as a technical detail, something that only mattered inside equations. But the scary part is the effects of these fluctuations have been measured. Tiny shifts in atomic energy levels, known as the Lamb shift, and the slight force that appears between metal plates in a vacuum, the Casimir effect, both point to the same conclusion. In other words, the void is alive with activity. The incredible part was the next step. If space-time and energy are boiling at the smallest scales, then a whole universe could, in principle, arise as a rare, long-lived fluctuation within this deeper quantum reality, not a deliberate creation, just one bubble that did not collapse immediately. What would have happened if that bubble had been slightly different or had died out in a fraction of a second is impossible to say. The result was this universe instead, expanding and cooling while the foam beneath continues its invisible turmoil. The idea is simple. If such a civilization ever exists, and if it runs not one, but millions of these simulated worlds, then simulated minds would vastly outnumber biological ones. In other words, most beings experiencing a universe like this would not be in the original base reality at all. They would be in carefully calculated imitations. Here is where things get uncomfortable. If that picture is true, then statistically it might be more likely that this particular universe is a simulation than the real thing. The scary part is that from the inside, the difference would be almost impossible to detect. The laws of physics, the expansion of space, even the quantum foam beneath space-time could all just be rules in someone else's program. In that scenario, beyond the universe would not mean another bubble of space or a higher physical dimension. It would mean a higher level of reality entirely, where this cosmos is nothing more than data patterns in a computer-like substrate. The cosmic microwave background, black holes, the birth and death of stars, everything would be entries in memory, updated step by step. The incredible part was how quickly this idea escaped philosophy seminars and moved into popular culture. Movies, novels, and even some technology leaders began talking openly about living in a simulation. For a while, it almost sounded like a new kind of religion, with programmers instead of gods and code instead of commandments. But most physicists do not treat this as a scientific theory. The thing is, a theory has to risk being wrong. It has to make testable predictions. A perfect simulation can be tuned so that any strange event, any anomaly, is just another line of code. The result was a framework that can explain everything in general and nothing in particular, which is pretty disturbing from a scientific point of view. There have been suggestions for tests, looking for pixelation in space-time or strange limits in high-energy cosmic rays, but so far nothing conclusive. And even if a glitch appeared, how could anyone be sure it was not just new physics, rather than evidence of a programmer cutting corners? So the question lingers. If every universe discussed so far can be reduced to patterns in something deeper, fields, quantum foam, or unknown mathematics, what actually counts as real? And if this is not the base layer, what would have happened if whoever built it decides to turn it off? Turning it off is one possibility. Letting it run until it can no longer change is another. Cosmologists have a name for that final frozen outcome: heat death. It sounds dramatic, but in other words, it is the universe's most boring possible ending. To understand it, start with a simple idea. Left alone, things spread out. Hot coffee cools as its heat leaks into the room. A drop of ink in water eventually diffuses until every part of the glass looks the same. That slow drift from concentrated, useful energy to thin, useless background is called increasing entropy. The thing is, entropy is not just a chemistry problem in a kitchen, it is a rule written into the universe itself. Over time, energy prefers to spread from where it is focused to where it is not. Stars shine because gravity has squeezed matter so tightly that nuclear reactions can run. Planets, storms, life, and technology all ride on the back of those temporary energy gradients. Here is where things get uncomfortable. Those gradients do not last. Given enough time, every star will run out of fuel. Galaxies that now blaze with billions of suns will fade into collections of dead embers, white dwarfs, and neutron stars slowly cooling in the dark. On even longer timescales, gravity keeps working. Some remnants fall into black holes. Others are flung out into the growing emptiness. For a while, black holes look like the final winners, swallowing whatever passes too close. The incredible part was when scientists realized that even black holes leak. Stephen Hawking showed that black holes should emit a faint glow, now called Hawking radiation. It is unimaginably weak, but given enough trillions upon trillions of years, the result was disturbing. Black holes themselves evaporate. The most massive ones, anchoring entire galaxies today, eventually dissolve into a thin haze of low-energy particles. Run the clock forward far beyond any human timescale, past the death of the last star, past the evaporation of the last black hole. What is left is not fire, but almost perfect uniformity, a near vacuum filled with a cold mist of stray particles and stretched out photons, each carrying so little energy that almost nothing can ever happen. The scary part is that this heat death is not hot at all. It is the point where temperature differences, pressure differences, any differences that could power a process or a mind have been erased. No free energy means no chemistry, no memory, no observers to notice that anything has ended. At that stage, the universe is not a place of events. It is a record that can no longer be edited. So the question changes. In a cosmos that has reached maximum entropy, what does beyond even mean? Beyond time, beyond change, beyond anyone left to ask whether there is anything on the other side of the dark. In that frozen record, nothing should ever happen again. But quantum physics quietly refuses to say never. Even in a heat-dead universe, the vacuum is not perfectly still. On the smallest scales, fields still jitter. Tiny random blips of energy appear and disappear. These are quantum fluctuations. Most of the time, the result is nothing. But given enough time, almost anything allowed by physics can, in principle, flicker into existence for a moment. The incredible part was how far some physicists pushed that logic. If particles can appear, why not atoms? If atoms, why not entire brains, complete with false memories of a life that never happened? This is the idea of a Boltzmann brain. A lone, self-aware fluctuation, drifting in a black, empty cosmos, convinced it once stood on a planet under a warm sun. Here is where things get uncomfortable. In some versions of cosmology, a heat-dead universe lasts for an almost unimaginable span of time, long enough that random disembodied minds could be produced far more often than full, low-entropy universes with galaxies and planets and biological evolution. In other words, statistics would say that most observers are not living beings with real histories, but brief, isolated hallucinations. The scary part is what that would mean. If Boltzmann brains dominate, then ordinary observers with genuine pasts become rare exceptions. Memory stops being evidence. Experience stops being trustworthy. The idea is so disturbing that many scientists treat it as a warning sign. If a theory predicts a universe ruled by fake minds with fake memories, something about that theory is probably wrong, but quantum fluctuations might do more than build nightmare solitudes. Some models suggest that, in a decayed vacuum, a rare fluctuation could nucleate a tiny inflating bubble of space-time. From the outside, it would be microscopic. From the inside, it would look like an entire expanding universe with its own arrow of time, its own Big Bang, and no awareness of the cold grave it budded from. Black holes add another disturbing possibility. As they slowly evaporate through Hawking radiation, the information they swallowed is believed to leak back out in scrambled form. Some proposals go further, suggesting that the extreme conditions near a black hole's core could tunnel into a new region of spacetime. The result was a kind of cosmic offspring, a baby universe branching off from a dying parent. For a while, these scenarios sound almost hopeful. Rebirth, renewal, a multiverse of fresh starts. But look closer. Any new region would be causally sealed off, its inhabitants forever unable to reach back or confirm the story. Identity becomes local. History becomes parochial. What counts as real collapses into whatever a given pocket universe can remember, and then comes the pattern interrupt. Because despite all these exotic escape routes, the most likely future, according to many calculations, is not a grand cycle or a graceful reset. It is an endless, almost featureless darkness where nothing happens for eons, until, very rarely, something does. Not a new cosmos full of stars, not a civilization, just isolated random horrors, a conscious brain blinking into awareness in the void, terrified, confused, and then gone again before it can even finish asking what just happened. But that nightmare brain in the dark assumes one thing, that the universe just keeps fading forever. What if it doesn't? Cosmologists have spent decades asking a disturbing question: how does all of this actually end? The result was a set of cosmic endgames that are very different from the quiet heat death. And each one changes what it even means to ask what lies beyond the universe. The first is called the Big Rip. On the surface, it sounds exaggerated. In reality, it is one of the scariest uses of the words dark energy ever proposed. Dark energy is the name given to the mysterious force driving the accelerated expansion of space. In other words, the gaps between galaxies are growing faster and faster. If that repulsive effect keeps strengthening, eventually it does something terrifying. First, galaxy clusters are pulled apart. Then individual galaxies are shredded, their stars flung away like sparks from a grinding wheel. Later, stars lose their planets. Planets lose their crusts. Closer to the end, even atoms are torn open as space itself stretches faster than the forces holding matter together. The scary part is, in a true Big Rip, there is no stable outside watching this happen. Space-time is ripped at every point. Beyond a rip is not another universe. Beyond a rip is nothing coherent at all, just a final, universal dismemberment of structure. The second scenario goes in the opposite direction, the Big Crunch. For a while, scientists thought this was the most likely ending. If there is enough matter, gravity can eventually win against expansion. The universe slows, stops, and then reverses. Galaxies that were receding begin to fall back together. Temperatures rise, radiation builds. Over unimaginable timescales, everything collapses into a denser and denser fireball until the cosmos returns to something like its own beginning, hot, opaque, and violently compressed. Here is where things get uncomfortable. If the universe ends in a crunch, what happens next? One idea is the Big Bounce. In a Big Bounce, that final collapse is not the end, but a trigger. The compressed state rebounds, igniting a new expansion. The result was a universe that dies into a crunch and is reborn into another Big Bang. Maybe not once, but over and over. In that picture, beyond this universe is not a quiet void. Beyond a crunch might be the birth of a new cosmos with different laws. Beyond a bounce could be an endless chain of universes, each one following the last like beats in a cosmic heartbeat. But current observations of dark energy point somewhere else. The numbers suggest expansion is not racing toward a rip or slowing toward a crunch. It is drifting toward a slow, cold fade. And yet, the incredible part was what those same measurements quietly imply about the vacuum itself. They hint that the fabric of reality may be metastable, balanced on a ledge, which raises a different, pretty disturbing possibility that the universe's end will not come from the large-scale fate of space at all, but from a tiny, invisible event that has already begun. Somewhere beyond the part of the cosmos any telescope can ever see. That invisible threat racing through the vacuum leads straight into something even more disturbing, because while scientists were trying to understand how the universe might suddenly end, they stumbled on evidence that its large-scale behavior was already doing something it should not be doing at all. In the late 1990s, two independent teams pointed their telescopes at a very specific kind of dying star. These were Type 1a supernovae, white dwarfs that explode with almost the same brightness every time. In other words, they work as cosmic yardsticks. By comparing how bright they looked to how much their light was stretched, astronomers could reconstruct how the universe had been expanding over billions of years. The expectation was simple. The expansion should be slowing down. Gravity from all the matter in the universe should be pulling everything back, at least a little. For a while, that was the quiet assumption behind almost every cosmology model. The result was the opposite. Those distant supernovae were dimmer than expected. They were farther away than they should have been if the expansion had been decelerating. The expansion of the universe was not slowing. It was speeding up. The scary part is that nothing in standard physics was ready for that. To explain an accelerating expansion, scientists had to add a new ingredient to the universe, an energy that does not clump into stars or galaxies, that seems to fill space smoothly, and that pushes instead of pulls. It was given a simple, unsettling name: dark energy. Here is where things get uncomfortable. If space is full of this energy, then as space grows, the total amount of dark energy grows with it. More space means more dark energy. More dark energy means stronger acceleration. The expansion feeds itself. One way to describe this is through something Einstein himself once wrote into his equations: the cosmological constant. At first, he used it to hold the universe static. Later, he abandoned it. Now it is back with a different role. Empty space itself has energy. Even in a perfect vacuum, there is a residual background, a kind of built-in pressure of the void. Quantum field theory actually predicts vacuum energy. The incredible part was how badly the numbers failed. When physicists estimate how much energy should be in empty space, the answer overshoots the observed dark energy by an almost unimaginable factor. Depending on the details, the mismatch can reach 120 orders of magnitude. That is a 1 followed by 120 zeros. It is, by many accounts, the worst prediction in the history of physics. Pretty disturbing for something that controls the fate of the cosmos. So what would have happened if the vacuum energy had been even slightly different? In many calculations, most possible values either rip space apart too fast for galaxies to form or crush it back down almost immediately. Our tiny non-zero dark energy looks suspiciously like a narrow safe zone drawn in the middle of chaos. They had no idea at first how to justify that. Eventually, some researchers reached for a drastic possibility: that there is not one universe but countless expanding regions, each with a different amount of vacuum energy. In that picture, dark energy is a kind of cosmic lottery ticket. Most draws produce empty, dead space. A few produce universes where stars and observers can exist long enough to ask questions. If that is true, then the accelerating expansion is not just a property of this universe. It is a clue that something else lies beyond it. And the next step in the argument leads to a place even stranger than a single cosmic bubble racing apart from within. The next step is not a new force or a hidden particle. It is a change in perspective that quietly moves the universe out from under human feet. This is the anthropic principle. In other words, the observation that any conscious observer will only ever find itself in a universe compatible with its own existence. That sounds trivial at first, almost like a word game, but when applied to the fine-tuned numbers that control cosmic evolution, it becomes something much more disturbing. Take dark energy as an example. It is the pressure in empty space that drives the accelerating expansion. The measured value is tiny, but not zero, balanced on an almost impossibly narrow ledge. The scary part is that if dark energy had been only a little larger, the expansion would have torn matter apart before gravity could pull it into galaxies and stars. In that alternate history, there would be no long-lived suns, no planets, no chemistry slowly assembling complex molecules over billions of years. Just a thin, ever-diluting fog of particles racing away into darkness. No one would ever be there to notice that anything was missing. If dark energy had been much smaller or gone the other way, turning attractive instead of repulsive, the result was different but equally hostile. The universe might have recollapsed quickly in a catastrophic big crunch, or formed structures so early and so violently that heavy elements and stable planetary systems never had time to emerge. Again, no observers, just a brief, chaotic flash. For a while, scientists tried to derive the exact value from elegant equations alone. A single theory that would say, unavoidably, that dark energy must be this number and no other. The incredible part was that most early calculations overshot the real value by factors of 10, then by factors of 10 to the 120th power. That gap is not a small mistake. It is an abyss. Here's where things get uncomfortable. In some versions of cosmic inflation and quantum gravity, there is not one universe but a vast multiverse, with different regions realizing different values of dark energy and other constants. Most of those regions expand too fast, collapse too quickly, or freeze in sterile simplicity. Only a tiny fraction land in the narrow range where galaxies, stars, and long-lived chemistry can exist. In that picture, observers naturally appear only in those rare, balanced pockets, and then look around, surprised, asking why the numbers are so friendly. They had no idea how many dead universes came before. To many scientists, this feels like giving up. A deep physical question has been replaced with a selection effect. Things look this way because otherwise no one would be here to see them. It explains the bias, but does it explain the universe or just explain away curiosity? And then the pattern breaks. Because if the anthropic view is right, most of reality is not just beyond the observable universe. It is beyond relevance. Almost every universe, every region, every history is forever dark and empty of witnesses. The next question is no longer just what lies beyond this universe, but whether this universe matters at all on the scale that really exists. If most universes are empty, then the disturbing question becomes this: does anything out there ever leave a mark big enough to see from here? On the largest maps of the cosmos, astronomers have found something that looks like an answer: gigantic, jagged walls of galaxies stretched across space like scars. One of the first to really shake confidence was announced in 2003, the Sloan Great Wall. It is not a single object, but a vast chain of galaxy clusters and filaments. From end to end, it spans about 1.4 billion light years. In other words, light would have to travel through it for longer than complex life has existed on Earth. For a while, some scientists quietly asked whether something that big was even allowed. The reason goes back to a simple guiding idea. On small scales, the universe is messy and clumpy, but on large enough scales, it is supposed to smooth out. This is the cosmological principle. It says that if someone could stand unimaginably far away and average everything together, the universe should look homogeneous and isotropic, the same everywhere, in every direction. The scary part is that structures like the Sloan Great Wall push right up against the limits of that assumption. Galaxies are not supposed to organize themselves into coherent features across billions of light years. Standard models say that random quantum fluctuations in the early universe grew into today's web of galaxies, but only up to a certain characteristic size. Then an even more disturbing candidate appeared. In 2013, analysis of distant gamma ray bursts suggested an enormous concentration of matter, now known as the Hercules Corona Borealis Great Wall. If it is real as a single structure, its estimated scale is around 10 billion light years across. That is a significant fraction of the observable universe itself. Here is where things get uncomfortable. If such a wall truly exists as one connected feature, it looks like a direct challenge to the cosmological principle. It would mean that even on the very largest scales that can be seen, the universe is not really smooth. The result was an immediate debate. Some researchers argue that these walls are illusions created by the human brain and by small data sets. Clumps that look continuous might actually be separate structures lined up by chance. In that view, they are rare statistical flukes, extreme but still compatible with the standard cosmological model. Others are not entirely convinced. The thing is, if a genuine structure spans such a huge fraction of the observable universe, it hints that the seeds for it were laid down extremely early, possibly before the phase of rapid expansion known as inflation had finished ironing out irregularities. That is where speculation turns outward. A few physicists have suggested that features like these might be fossil traces of pre-inflationary physics, or even subtle tidal influences from beyond the part of space that can ever be seen. If another region or another bubble once pressed against ours, what would have happened to the pattern of matter inside this one? The incredible part was that nothing about daily life changes when a new Great Wall is announced. The night sky looks the same, but in the background, the map of the universe becomes less certain. Whether these structures are impossible or just improbable, they are a reminder of something pretty disturbing. All of cosmology is being reconstructed from one tiny local vantage point. The next step is to ask what happens if that vantage point is not typical at all. All of this assumes the map can eventually be filled in. It can't. Not because telescopes are too weak, but because the universe itself draws lines that nothing can cross. The first line is called the particle horizon. In simple terms, it is the maximum distance from which light has had time to reach this region of space since the Big Bang. The thing is, the universe is 13.8 billion years old, but the observable radius is about 46.5 billion light years, because space has been stretching the whole time. Light has been running. The track beneath it has been moving. The second line is more disturbing. It is the event horizon of the universe, not a solid wall, but a boundary in space-time. Beyond it, events happening right now will never affect this region, not even if the cosmos lives forever. In other words, it marks the difference between in principle reachable and gone forever. To see how that happens, imagine two ships on an ocean that is not just rough, but expanding. Each ship turns on its engines and heads toward the other. For a while, the distance shrinks. Then the expansion rate increases. Eventually, the water between them stretches faster than the ships can sail. They can still see each other's old signal lights frozen in time, but any new message sent now will never arrive. That is what accelerated expansion does on the largest scales. Dark energy pushes galaxies away faster and faster. The incredible part was how fast this acceleration turned out to be when it was discovered in the late 1990s. The result was a universe in which the event horizon in so-called co-moving coordinates is effectively shrinking, cutting off more and more distant regions, even as space itself gets larger. Here is where things get uncomfortable. There are galaxies visible in telescopes today whose present versions are already beyond the event horizon. Their light left billions of years ago, when contact was still possible in principle. But while that light was in transit, expansion pushed them over the boundary. Any signals sent toward them now will never catch up. The scary part is that their current state is already sealed off, permanently outside this region's causal future. In other words, much of the night sky is made of ghosts. Real galaxies, real stars, real planets, but only as they were. Their now can never touch this now. No future technology, no hypothetical drive, no clever shortcut in normal spacetime can change that. So if a single universe already hides most of itself behind these horizons, what happens when the questions get even bigger? If this cosmic bubble is just one of many, scattered through an inflating multiverse, how can any observer trapped behind an event horizon ever know whether everything seen is a lonely exception or just one disturbing experiment among countless others still completely out of reach? For a while, it sounded like the story should end there, trapped in one cosmic bubble, cut off from everything beyond. But inside that bubble, scientists have been running a quiet, disturbing experiment of their own, trying to see if space itself secretly folds back on itself. The thing is, a universe can be finite without having an edge. Imagine flying forever in one direction and eventually ending up back where you started. That is a multiply connected universe. No wall, no cliff, just a cosmic loop. If reality is built like that, there should be fingerprints left in the oldest light in existence. That light is the cosmic microwave background, the faint afterglow from when the universe was only 380,000 years old. It covers the entire sky as a mottled pattern of slightly hotter and colder spots. On the surface, it looks random. But the scary part is, if space wraps around on itself on a scale smaller than the observable universe, the same regions of plasma could be seen more than once. In other words, the sky should repeat, not in obvious wallpaper tiles, but in precise matching rings. These are the so-called circles in the sky tests. Scientists take full sky CMB maps and algorithmically search for pairs of circles with the same temperature fluctuations, offset and rotated, as if light had taken two different routes through a finite cosmic hall of mirrors. For a while, there were hints, statistical oddities, suspected alignments. If those circles had been confirmed, the result was going to be incredible. Direct evidence that the universe is smaller than it looks, wrapped back on itself in some higher dimensional way. But eventually, as the data improved from COBE to WMAP to Planck, those early claims faded. No convincing circles, no clean repetitions. The same hunt moves into 3 dimensions with galaxy surveys. Projects like the Sloan Digital Sky Survey map the positions of millions of galaxies,
Mhm.
tracing out an enormous foam of filaments, walls, and voids. It looks chaotic, but hidden inside that chaos, a small multiply connected universe would imprint repeating patterns, galaxy structures seen again and again at different distances and directions. Here is where things get uncomfortable. So far, those repeating structures are not there either, at least not in any way that survives serious statistical scrutiny. The result was another constraint. If the universe does wrap, the fundamental domain, the size of the repeating cell, must be larger than the entire observable universe. That sounds reassuring until the methodological limits come into focus. Beyond a certain scale, the data simply stops. The CMB is a wall of fog beyond which no earlier light can be seen. Galaxy surveys fade into noise and darkness. Past that horizon, any global topology becomes effectively untestable. Then comes the pattern interrupt. After all the sophisticated algorithms, all the sky maps, all the surveys, the most basic question, what is the actual shape of everything, may be permanently out of reach. The universe might be infinite, or it might loop back on itself just beyond the last photon anyone will ever detect. And from inside this bubble, there may be no experiment that can ever tell the difference. From there, the questions stop being about distance and start being about time itself. Because right at the beginning, the usual rules of space and time simply fail. At extremely high densities and temperatures, general relativity breaks. The equations that describe planets, stars, and galaxies spit out an infinite, a singularity, and then stop. The scary part is, this happens exactly where the universe is supposed to begin. In other words, the main tool used to describe the cosmos cannot describe its own first moments. That is why scientists have spent decades trying to merge relativity with quantum mechanics into a single framework, a quantum theory of gravity. For a while, that search was mostly theoretical: strings, loops, higher dimensions, complicated mathematics with almost no data. But eventually, some of these ideas led to a disturbing possibility. Maybe there was never a sharp first instant at all. One of the most famous attempts is called the Hartle-Hawking no-boundary proposal. It starts with something deceptively simple. Near what is called the beginning, time might not behave like time. Imagine approaching t equals 0 and finding that the direction usually called before and after gradually turns into something more like left and right. That is the basic idea. Time becomes space-like. The result was a model where the universe is finite in extent, but has no edge in time. The thing is, this is not just poetic language. Mathematically, the geometry is similar to the surface of a sphere. The surface is finite, but walking in any direction never reaches an edge. There is no last point where the planet suddenly stops. In a no-boundary universe, the Big Bang is less an explosion from nothing and more a smooth rounding off of space-time. Here is where things get uncomfortable. If the start is a rounded cap instead of a sharp corner, then the question, what happened before the Big Bang, may simply not apply. It is like asking, what is north of the North Pole? The words make grammatical sense, but the concept they are trying to point to does not exist in that geometry. There is no further north because north itself ends there. Some quantum cosmology models go even further. They suggest that the universe could have emerged from a quantum fluctuation in a timeless state, or that time itself is an approximate property that only appears once the universe is large and classical enough. Before that, there is no clock to tick, no sequence to arrange events. The incredible part was how quietly this rewrites the original question. If time is not a backdrop but a feature of this particular universe, then whatever lies beyond it might not be earlier or later at all. It might be something that current language and current physics are not built to describe. And if that is true, then the next disturbing step is obvious. Maybe the Big Bang was not the only such event. If the Big Bang was not unique, then the universe that feels like everything might only be one region inside something larger. To understand how disturbing that is, it helps to look at a smaller, darker version of the same problem. A black hole is not just a dense object, it is a place where space and time are bent so far that there is a point of no return. That invisible boundary is called the event horizon. In other words, cross that surface, and every possible path through space-time leads inward. Classically, information, light, matter, entire stars can fall through it. Nothing comes back out. For a while, that was the end of the story. Matter falls in, a black hole grows, and the rest of the universe only sees a dark, silent region. The scary part is what happens when quantum mechanics is added. Quantum theory says information cannot be truly destroyed. Even if it is scrambled beyond recognition, the microscopic details of what fell in are supposed to be preserved in some way. But a black hole seems to erase those details behind its horizon. When Stephen Hawking showed that black holes should slowly evaporate by emitting radiation, the result was a paradox. Hawking radiation looks almost perfectly random. If the black hole completely disappears in the end, where did the information about everything that fell in actually go? If it is gone, basic rules of quantum physics break. If it is not gone, then it must somehow be encoded in the radiation or on the horizon itself in a way that current understanding does not easily explain. Here is where things get uncomfortable. To fix this, some physicists proposed that a three-dimensional region might be fully described by data living on a two-dimensional surface. This idea is called the holographic principle. The incredible part was that certain black holes in higher dimensional theories really do behave as if all their internal information is written on their boundary. This is more than a mathematical trick. It suggests that, at a fundamental level, reality inside a region could be a projection of information stored on its edge, a volume acting like a hologram of its own surface. Now scale that idea up. The observable universe also has a boundary, a cosmic horizon, about 46.5 billion light years away in every direction. Beyond that, light has not had time to reach us. It is a one-way surface in practice. Signals go out, but anything that happens beyond it cannot send a message back in. The thing is, the parallel is hard to ignore. A black hole has an event horizon. The universe has a cosmic horizon. In both cases, there may be a deeper description where what is inside is encoded on what can be seen at the boundary. Some researchers have even asked a disturbing question. Could the entire visible cosmos be like the interior of a gigantic black hole embedded in a higher dimensional space? If that is even close to true, then what lies beyond might not be more space in the usual sense. It might be written in some alien language of physics on an edge that can never be crossed. And if the universe is the inside of something else, the next question is unavoidable. What would have happened if that outer structure changed or collapsed? That collapse question hides something even stranger. Because in some of the most radical ideas in modern physics, the universe is not the inside of a larger object at all. It is the shadow of something written somewhere else. This is the holographic principle. In everyday terms, think of a flat plastic card that shows a three-dimensional image when light hits it. The card is two-dimensional, but it somehow encodes a 3D scene. In other words, a lower dimensional surface can secretly contain all the information about a higher dimensional world. The scary part is that some scientists now think the entire universe might work that way. Not just a picture, not just a trick of light, but all of space, every volume of it, emerging from information stored on a distant boundary. This idea did not come from philosophy. It came from black holes. For a while, physicists assumed that the information describing matter falling into a black hole would disappear forever. The result was a paradox because quantum theory says information cannot be destroyed. Here is where things get uncomfortable. Detailed calculations showed that the amount of information a black hole can hold does not scale with its volume. It scales with the area of its event horizon. The surface, not the inside. That is pretty disturbing if space is supposed to be made of smooth, continuous volume. Eventually, a new picture emerged. Maybe a black hole is like a hologram, with everything inside encoded on its boundary. The incredible part was that this logic was then pushed further. What if entire regions of the universe behave the same way, not just black holes? In the late 1990s, theorists found a concrete example. It is called the ADS/CFT correspondence. On one side, there is a universe with gravity in a kind of curved, higher dimensional space. On the other, a lower dimensional system without gravity, living on the boundary, described by quantum fields and pure information. They had no idea at first that this mathematical relationship would become one of the most studied ideas in theoretical physics. The thing is, ADS/CFT is not a direct model of the real cosmos. It uses a special kind of space, not the expanding universe seen through telescopes. But as a proof of concept, it is brutal. It shows that what looks like a full 3D universe with gravity can be completely equivalent to a lower dimensional description with no gravity at all. Space, depth, interior, all of it can be emergent. If that is even close to how reality works, then everyday experience is misleading at the deepest level. It does not mean the world is fake, like a cheap simulation. It means that the most fundamental description of it might be written in a language that has no distances, no volumes, only relations between bits of information. So the usual question starts to break. Instead of asking what is beyond the universe, holography forces something more unsettling. What is beyond the code that defines the universe? And what would have happened if that code had been different? At some point, the universe just stops answering. For a while, it feels like more data will fix everything. Bigger telescopes, better detectors, faster computers. But the thing is, the barriers that appear now are not just technical. They are woven into the structure of reality itself. One of them is already visible every clear night: the observable universe. A sphere about 46.5 billion light-years in radius, defined not by where matter ends, but by how far light has had time to reach us. Beyond that cosmic horizon, galaxies continue, space continues, maybe forever. But any signal from there will never arrive. In other words, most of reality is already sealed off behind a wall that no technology can cross. Shrink the scale instead of expanding it, and another wall appears. At distances near the Planck length, the familiar picture of smooth space-time breaks down. Quantum fluctuations become violent. Geometry dissolves into something like a foaming chaos. Below that, current physics stops making sense. The scary part is, any answer about what is really there might be permanently hidden, because probing it directly would require energies that would collapse into black holes before revealing anything. Then there is the uniqueness of this particular cosmic bubble. Cosmic inflation says the observable patch is just one region inflated out of a much larger structure, maybe one of countless bubbles, but there is no way to step outside this one and compare. The result was a disturbing realization. Us questions about the global shape of all of space or the total number of universes might be unanswerable in any empirical way. So, how do scientists stop this from turning into pure storytelling? Here's where things get uncomfortable. Healthy speculation is chained, however loosely, to observations. A multiverse model might predict a specific spectrum of cosmic microwave background fluctuations or a certain pattern in how fundamental constants could vary between bubbles. If those patterns fail, the idea is wounded. Unfalsifiable stories, by contrast, can survive every possible observation unchanged. They are safe. And that is precisely what makes them scientifically useless. The incredible part was how unsettling this becomes on a human level. Entire civilizations can stare across billions of light years, map the afterglow of the Big Bang, and still never know whether space wraps around on itself, whether other universes crash into ours, or whether a higher dimensional structure surrounds everything. Above all of this sits inflation, that brief, almost unimaginable burst of expansion. Its strength, its duration, even the spectrum of quantum fluctuations it amplified were all parameters that could have gone wrong. Little more dark energy, and space races apart so fast that galaxies never coalesce. A little less, and everything recollapses into a universal black hole before chemistry has time to start. The incredible part was that every stage, from the first fractions of a second to the quiet glow of the present, is balanced on this knife edge. Change the quantum noise at the beginning, and another bubble universe forms with different constants, different histories, and no observers. Our reality is just one successful throw in an ocean of failures. That is already pretty disturbing, but it raises a new question that almost no one is comfortable with. If existence so far is a chain of near misses, how stable is that balance going forward? And what happens if the next cosmic almost does not miss at all? That balance might not just be fragile, it might be temporary. In many modern models, the basic features that feel absolutely solid, the strength of gravity, the charge of the electron, even how many spatial dimensions are unfolded and usable, are not permanent fixtures of reality. They are local settings. In other words, the universe looks the way it does because the underlying vacuum settled into one particular state for a while. The scary part is that this vacuum is not guaranteed to be the lowest, safest possibility. In quantum field theory, what seems like empty space is more like a landscape of potential energy levels. A universe can get trapped in a false vacuum, a metastable state that behaves stable on human timescales, but is ultimately just a temporary arrangement. To see how unstable things can be, it helps to go back to the early universe. Right after the Big Bang, temperatures and energies were so extreme that forces and particles behave very differently. What now appears as four separate forces may have been merged into one. As the universe expanded and cooled, it passed through a series of cosmic phase transitions, like water freezing or boiling, but on a terrifying scale. During those transitions, symmetries broke, particles gained mass, the electromagnetic and weak forces split. The result was the specific set of rules that allow atoms, stars, and eventually observers to form at all. But here is where things get uncomfortable. There is no reason to think that process is over forever. In some scenarios, another phase transition could still be waiting. A tiny bubble of a lower energy vacuum could appear somewhere beyond the observable universe. It would expand at nearly the speed of light, rewriting the laws of physics as it passed. There would be no warning, no defense, and no survivors. The result was always the same in those calculations. Everything recognizable is erased. One way to picture it is disturbingly simple. Imagine a lava lamp in a dark room. Blobs of wax rise, stretch, merge, and break apart. Each shape looks stable for a few seconds, then melts into something else. Our entire cosmos, with its galaxies and physical constants, could be one of those shapes. Briefly coherent, then gone, while the deeper flow continues. The incredible part was how quickly this idea shifted the mood among some scientists. The universe stopped looking like a solid stage and started to resemble a passing fluctuation in a much larger, mostly unreachable reality. If the vacuum, the forces, and even the number of dimensions can change, what exactly counts as permanent anymore? It would be comforting to say that the danger is only theoretical, that this arrangement will last forever. But the thing is, the equations do not promise that. They only describe how things behave until the next transition. That means our entire universe might be less like a building and more like a wave crossing a deep, unseen ocean. And waves, no matter how impressive, do not get to decide when they end. From inside that wave, everything looks strangely calm. The sky tonight seems permanent, the stars unhurried, as if this arrangement of matter has always been here and always will be. It has not, and it will not. So the universe looks calm only because the camera is frozen on a single frame. For a while now, this video has stayed on that frame and slowly pulled back, revealing how bad the wider shot really is. Then there is the stranger beyond, outside this space-time patch entirely. Inflation theory suggests that this universe might be only one bubble in a vast, eternally inflating multiverse. Other bubbles could have different physical constants, different particles, even different numbers of dimensions. The scary part is that collisions, if they happened, are either erased by expansion or hidden beyond the horizon. Those other regions are not just far. They are fundamentally unreachable. Another boundary lies inside the laws themselves. Physics textbooks quietly assume that the vacuum is stable, that the current rules of quantum fields will hold forever. But some calculations hint at a metastable vacuum, a false floor. If a lower energy state exists, a bubble of truer vacuum could appear somewhere beyond any telescope, race outward at nearly light speed, and rewrite every law of nature as it passes. No warning, no defense. Here is where things get uncomfortable. Beyond this fragile set of rules is not a place, but a different game board entirely. Finally, there is the beyond of time. What happens after the last usable energy is spent? In a heat death scenario, galaxies drift apart, stars die, black holes evaporate, and the universe thins into near perfect uniformity. Beyond that is not a new chapter. It is the absence of chapters. The result was a cosmos that, given enough time, forgets it ever made anything complex at all. Across all these versions, beyond is not a clean edge in space. It is a perimeter around influence. There are regions that can never be reached, laws that cannot be chosen, futures that cannot be escaped. That sounds crushing. For a while, philosophers and scientists worried it might make meaning feel small. But the incredible part was the opposite conclusion. Knowing the universe is vast, cold, and indifferent does not erase significance. it localizes it. The sphere of control is tiny, but real, and uniquely tied to this planet, this civilization, this brief window before entropy wins. Pattern interrupt. Imagine the multiverse is real, infinite, filled with copies and variations. What would have happened to meaning then? Strangely, nothing changes here. This single timeline is still the only one that can be acted in. The thing is, the abyss beyond does not compete with this moment. It frames it. Against an endless, uncaring backdrop, a thin film of awareness on one small world stands out more sharply, and the responsibility to protect it becomes harder to ignore. That thin film is all that stands between awareness and a universe that does not care whether it exists at all. By now, the outlines of that universe look very different from the calm night sky overhead. Somewhere beyond the 46.5 billion light-year horizon, there are regions that will never send a single photon here. Not eventually, not ever. The expansion of space is pulling them away faster than light can cross the gap. In other words, most of what exists is already unreachable. Entire chains of galaxies, vast walls, and voids are sliding over a one-way boundary. Information goes out, nothing comes back. The scary part is that anything happening out there might as well be happening in another reality. Here is where things get uncomfortable. Some physicists think those other realities might be literal. In eternal inflation models, space does not just expand. It keeps spawning new bubbles of space-time. This universe is one bubble. Beyond it, others form, collide, and die. A collision scar might already be written across the cosmic microwave background, a faint bruise from another universe brushing past. The result was a disturbing shift in perspective. The Big Bang stops looking like a unique creation event and starts looking like one flash in an endless storm. For a while, scientists tried to see whether this multiverse could be tested, mapped, turned into data. The thing is, even the most optimistic versions leave most of those other universes permanently sealed off. And even this bubble is not safe. The vacuum that fills it might not be the lowest possible energy state. Somewhere, beyond any telescope's reach, a tiny region could tunnel into a more stable vacuum. That seed would expand at almost the speed of light, rewriting the laws of physics as it went. No warning, no time to react. By the time it arrived, everything would already be gone. If that does not happen, heat death waits instead. Stars burn out. Black holes evaporate. Matter decays into a thin wash of cold radiation spread across an ever larger volume. No structure, no chemistry, no minds. Just a dark, dilute, afterglow stretching on for unimaginable timescales. Now zoom back to the present moment. A small lit platform hangs in the dark. One planet in one galaxy inside one temporary bubble of space-time. Around it, the darkness is not just empty space. It is unvisited time, unreachable scales, unrealized possibilities. Above, the unobservable universe. Beside it, hypothetical colliding bubbles. Ahead, vacuum decay or heat death. Feeling small in the face of that is not a mistake. It is a rational response to the numbers involved. Against a background this large, any single life, any single world looks almost invisible. But insignificance on a cosmic scale does not cancel significance on a human scale. Both can be true at once. The incredible part was always this: meaning only needs to exist where it is experienced. A conversation, a decision, a shared look at the sky occupies almost no volume in space-time, yet it can still redirect a lifetime. So the platform stays lit. The question is what to do on it. If this journey has changed the way the night sky looks, there are concrete ways to keep pushing into the dark and to help others see what is really hanging above their heads. Here is where things get uncomfortable. The instinct is to back away, to click on something lighter, to let the mind slide back into smaller problems. Instead, there is another option. Sit with it. The image of that 46.5 billion light year bubble is not just a graphic. It is a hard limit on what any creature made of matter and light can ever know. Pausing on that frame, on that faint sphere pushing against blackness, is a way of feeling the cage that physics quietly built around every thought. The same goes for the moment the camera pulled back from galaxies to show the cosmic web fading into darkness. That cut was not just dramatic. In other words, it was a reminder that most of reality, if it exists, is already gone from reach forever. Letting that sink in for a while is disturbing, but it is also honest. The scary part is how different minds react. For some, the idea of an infinite, edgeless universe is the worst version of beyond. For others, it is the bubble universe, surrounded by other bubbles that will never be seen. And for a few, the most unsettling picture is the quiet heat death where every star goes out and nothing new ever happens